Good morning, dear students. In the last video, we have seen that alkenes and alkynes are also functional group isomers of each other. Alkenes, if present at two positions, then they will be dienes. So here let's have an example. CH2 double bond CH, CH double bond CH2. Here we have one double bond, here we have one more double bond. So in this organic compound, we have at two position double bonds, right? What is the molecular formula? C4H6. In the same way, see here also CH triple bond C, CH2, CH3. Here also C4H6 molecular formula same. But here there is no double bond. Instead of that, there is one triple bond, right? That means diene and alkynes having same molecular formula, but now if we see their functional is different with alkene series and alkyne series. It is buta-1,3-diene, whereas it is but-1-ine. Thus, dienes and alkynes are functional group isomers of each other. Functional groups are isomers of each other means they have similar formula but different structural formula and also different properties, because they have different function groups and due to that they have different structure formula, and because their functional groups are different, their properties are different. Here I have mentioned few different properties. See here, alcohols and ethers. In the last video we have seen that alcohols and ethers are also isomers of each other, but their properties are different. Alcohols show hydrogen bonding, whereas ethers do not show hydrogen bonding. Alcohols are soluble in water, ethers are not soluble in water. Alcohol's boiling point are much more compared to ethers, right? Ethers are not soluble in water and thus they are organic solvents. Alcohols are more reactive than ethers and ethers are less reactive than alcohols. In the same way, aldehydes are more reactive than the ketones. Aldehydes and ketones are also the functional group isomers. Thus, in chain isomers and position isomers, first and second type of isomers, only structures are different. When we have seen chain isomers and position isomers, molecular formula was same, but their structures were only different. So their physical properties are different, but chemical properties are same. But in functional group isomer, molecular formula are same, but their structure as well as functional groups are different. And so their chemical properties are also different. So this was about the functional group isomers. Now the fourth is metamerism. What is metamerism? The compounds having same molecular formula but different number of carbons on either side of functional group is termed as metamerism. See, one thing is common when we are learning isomerism. In all types of isomerism, molecular formula remains same, right? In chain isomers, the difference in the chain was there. In position isomers, there was a difference in the position of the groups. In functional group isomers, molecular formula was same, but functional groups were different. And in metamerism now, molecular formula is once again same, but the number of carbons on either side of functional group is different, right? Let us see as an example. Here is CH3CO, CH2, CH2, CH3. So how many carbons? 1, 2, 3, 4, 5. From this side, this is second carbon. From this side, it will be the fourth. So the name is pentane 2-one. So how many carbons? 1, 2, 3, 4, 5. And hydrogen 3, 4, 5, 6, 7, 8, 9, 10. Let us see here 1, 2, 3, 4, 5. 3, 4, 5, 6, 7, 8, 9, 10. 5 carbon, 10 hydrogen. But here you see the attachment is on the third position. So it is pentane 3 on. Right? Molecular formulas remain same. But what is the thing? Here on this side only one carbon is there. Here 1, 2, 3 carbon is there. Either side of the functional group, number of carbon are different. Here 2, here 2, right? Now let us see here. CH3O, CH2, CH2, CH3. It is oxy-ether group. So lesser number of compound will take O. So it is methoxypropane. And here it is either side is same. So it is ethoxyethane. So we have to compare this two. Don't compare here that here also 2 and here also 2. Here also 2 and here also 2. We have to compare this with this. Here one side 1 and another side 3. Whereas here both the side 2. So comparison is between these two. Here also 1 and 3. So compared to this it is different. Right? So thus these are the metamers of each other. When a group is having on either side a different number of carbon but same molecular formula, then it is a metamerism process and the the compounds are called metamers of each other. Now see, as per our textbook, we have 4 classification: chain isomers, position, functional group and metamerism. But here I will discuss the 5th one, and that is the tautomerism. It is a special kind of functional isomerism in which isomers differs in the arrangement of atoms but exist in dynamic equilibrium of each other. See, it is little different, and so it is termed as it is special kind of functional isomerism where the isomers differ in the arrangement of atoms. There is the different arrangement of atoms and they exist in the dynamic equilibrium. Dynamic equilibrium, it means moving. Equilibrium, that means in an equal rate. So when reaction takes place in the forward and backward reaction, when the moving of the electron is similar with the same rate, then it is termed as dynamic equilibrium. When we'll see the examples, it will be easily understood to you. Let us see. Basically, in the tautomerism, one hydrogen atom and one pi electron cloud shifts simultaneously. What does this mean? In tautomerism isomerism, one hydrogen atom and one pi electron cloud. Pi electron cloud, it means where the double bond is present in the compound. On that double bond, the cloud of electrons are termed as pi electron cloud. So the shifting, that means to move from one place to other. So hydrogen atom and pi electron cloud will shift simultaneously. Simultaneously, it means both at the same time. If one is going from here, at the same time the other will go from there. See, here is an example. Here is CH3, CH2, and on C here is double bond O. That means ketone group. If we give the name, it is 1, 2, 3 propane. Second carbon, ketone is there, so propane 2-O. Now here see, I have shown an arrow. Out of this 2 double bond, 1 double bond, pi electron cloud, right? Just now I told pi electron cloud is present on double bond. So this 1 double bond will shift here at the same time, simultaneously, at the same time. One of the hydrogen, see here I have not written CH3, CH2 and 1 hydrogen. So you will easily understand. One of the hydrogen will shift over here. So what takes place? CH3, C, this double bond has shifted here. So it is double bond and H is shifted here. So it is OH. So again what happened? It remained propane only, 3 carbon. But now there is here double bond. So numbering will go first to double bond 1, 2, 3. So prop 1 in 2 all. Right? So here I have shown double arrow, double headed arrow. It means both are in the dynamic equilibrium of each other. Both can convert from one form to another form, and in that their forward and backward rate remains equal, and that is why it is called they are in dynamic equilibrium. Now here what happened? This is ketone group. Ketone is converted to two different groups, ene as well as all. So it is enol. So it is said that ketone converted to ene and all. This is keto-enol tautomerism. What is it? Keto-enol tautomerism. Clear? One more example. Here is a cyclo compound. So here it is 1, 2, 3, 4, 5, 6. And C6 at 6. But no double bond, so it's not benzene. It's not hexene. It is cyclohexane. But here C double bond O is there. So it is cyclohexanol. Now see, this double bond will come here. It will be shifted here. At the same time, the hydrogen will shift from here to here. So what takes place? Here it will be double bond now, and this will be alcohol group. So as double bond is there, it is not now hexane. It will be hexene, cyclohexene, and here, so hexenol, cyclohexenol. They are also in the dynamic equilibrium of each other. As I told, what is dynamic equilibrium? Here also I have explained. Here, this double arrow shows that they converge in one another form, and so they are called dynamic equilibrium. What is dynamic equilibrium? Just now I explained, and still I have written here, pay attention. Dynamic equilibrium means moving in similar rate, that is equally in forward and backward reaction rate. The most common tautomerism is undergone by the group ketone and enol functional group. So keto-enol tautomerism is the most common tautomerism, right? So these are the 5 isomerism which falls under the category of structural isomerism. And now the second type of isomerism, the very first classification, recall it. Isomerism, basic 2 types, structural and stereo. So structure we have undergone 5 types: chain isomers, position isomers, functional group isomers, metamers, and tautomers, that is tautomerism. And now the second type is stereoisomerism. What is stereoisomerism? The compounds having same molecular formula but differ in relative positions of atoms or group of atoms in space. In space, that means whatever the possible surroundings is there. Or we can say the different arrangement of atoms in space. Compounds having same molecular formula, but there is a difference in the arrangement of the atoms or group of atoms in the space is termed as stereoisomerism. This also, to hear about isomerism, stereoisomerism, then chain isomerism, position isomerism, it is little similar to listen, but when we undergo the examples, we easily can clarify their meanings. Here also we will see the examples, so it will be easily clarified. Stereoisomerisms are of 3 types. They are geometrical isomerisms, conformational isomerisms, optical isomerism. Here we will see geometrical isomerism and conformational isomerism. Optical isomerism in a depth you will learn in your 12th classes, right? But let us see now geometrical isomerism. The word gives us the geometry. Geometrical, that means which will give us idea about geometry. That means in how way the structure will differ. What will be the difference in the geometry of the structure? That will be the geometrical isomerism. Geometrical isomerism rises, it takes place due to restricted rotation about carbon double bond carbon. Right? Now, rises due to restricted rotation. What is restricted rotation? Restricted rotation means electron clouds of double bond will entangle with each other and no further rotation will be possible. Entangled, that means to get mixed with or to get obstacle of each other. When one is moving, when other will be an obstacle to the first one, then they won't move further, then it is called entanglism. So, when electron clouds, that means when double bond is between the carbon and those two are trying to rotate, and because of the double bond between them, there will be no more space around to rotate, then they will experience obstacles and no more further rotation will be possible. It is called restricted rotation. Right? Here, this is the upper hand. So, like this. So, it is the upper carbon and this is the lower hand. So, it is the lower carbon. Between these two carbon, you see the two different pen I have taken, blue and red. It means it is a double bond. Now, the upper carbon remains stagnant. Stagnant, that means it will not move. And the lower will try to move. See here. So, what happened? This much rotation is possible. Now, further rotation is not possible. There is the obstacle of electron clouds between them. And this type of rotation is called restriction rotation. And because of this restriction rotation, the obstacle which comes due to that, these two bonds are entangling each other. Entangling, that means they feel that one is an obstacle for me, the other feel that another is obstacle for me. And this obstacle is called steric hindrance. This steric hindrance is responsible for the restriction rotation, and due to that there is again a two type of geometrical isomerism, which is cis and trans. Clear? So here is the restriction rotation. I hope you now understood what is restricted rotation. So some conditions are there which are essential for geometrical isomerism. What is it? First is presence of C double bond C. Right? So until and unless if there is no presence of carbon double bond carbon, then geometrical isomerism is not possible. And second, two groups attached to the same carbon should be different. That means their position can become different. There should be carbon double bond carbon and the groups present on the carbon should be different. These are the two essential conditions for geometrical isomerism. See, here is an example. See, the first condition is fulfilled, C double bond C. Here also C double bond C. Now here see, on this carbon one group is A, another is B. For this carbon also one is A, another is B. So possible. Second condition is two groups attached to the same carbon should be different. Here also see, this is A, this is B, this is A, this is B. Right? Now I just told that what happens? Here on keeping upper carbon stagnant, I just shown, right? Upper carbon stagnant, that means upper carbon will not move. And lower carbon start to rotate. Then two geometric takes place, that is cis and trans isomers. What is cis isomers? When two similar functional groups are on the same side, here see both A are on the same side, both B are on the same side. So here two functional groups are on the same side, then such isomers are cis isomers. And if two functional groups are on the opposite side, then they are called trans isomers. Clear? Here A is opposite to A, or if we see B, then B is opposite to B. Trans isomer. So these are the two geometric isomers. I just told what is geometrical isomers. There will be some difference in the geometry, and see the difference, right? Let us see further. In geometrical isomerism, when both functional groups are on the same side, it is cis isomer, and if both the functional groups are on the opposite or on the different side, then it is trans isomer. See, here is an example. It is C double bond C. So first condition is fulfilled. Double bond should be there between two carbon. Okay, now see, two on the same carbon, both the groups should be different. Yes, it is alcohol, it is methyl. Alcohol, methyl, both are different, both are different. So now see, here if we consider as a continuous chain, then 1, 2, 3, 4. 4 carbon are in a chain, so it is butane family. Now 1, 2 on second carbon, that is double bond, so it is but2ene. On this second alcohol, on third alcohol, so 2,3-diol. Now see here, both the alcohol are on the same side of the geometry, so it is cis but2ene 2,3-diol. Here see the same thing, but here now see difference. The carbon is here 1, 2, 3, 4. Again 4 carbons, so but. Second carbon ene, but2ene. Alcohol also see here on second, here on third. So that is also same 2,3-diol. But here on the same side, see here is alcohol, it is methyl. If we see this side also, then it is alcohol, methyl. On the same side, both are different. And if you see that they are opposite to each other, this to this and this, so it is trans isomer, trans geometry, trans but2ene 2,3-diol. This is the same example for butene, that is but2ene in a cis, right? Same side having the methyl group. Here it is opposite, right? So trans. So let us see for but1ene. There is a possibility of geometric isomers? Now if this is given a example to us, first of all we will go for the straight chain structure. So but1ene. So I will have 4 carbon first, and on first carbon I want double bond. So CH2 double bond, CH, CH2, CH3. Let us now give this straight chain a geometry. So what happened now? I want to give geometry. So first C double bond C, I will take C double bond C. This will be my first carbon. So it is CH2, CH2. Now first, second. So this is second carbon will be CH. Then what happened to third and fourth? So on second I will give third and fourth. So it will be my straight chain now. 1, 2, 3, 4. Now see first condition. C double bond C is present. Correct. Now on the same carbon both groups will be same. Sorry, different. Here it is different. Here is a hydrogen atom, whereas here it is ethyl group. But what about this carbon? Both are same. That means condition is not fulfilled and geometrical isomerism is not possible. Here on first carbon, or you can say upper carbon, both are hydrogen atoms. So geometrical isomerism is not possible because both are same atoms. Right? Let us see one more example. Pent2ene. So our straight chain will be CH3, CH2, CH, double bond, CH, CH3. So if I start from here, first and second carbon double bond is there. Now what is here? Let us see. CH3, so first take these two carbons, C double bond C, C double bond C, right? So this is CH, CH and CH3 methyl group. And what is left here then? Ethyl group, right? Now what we can say? This is the carbon, both are separate, different. This is carbon, both are different. So here geometric isomerism is possible, right? Now see here, how we can say that this is cis. If we say this is methyl, this is ethyl, though it is methyl and ethyl, right? Carbon different, but the group is similar. How? Because it is also alkyl group. It is also alkyl group. And as both are from the same family of alkyl, that means they are considered as the same group member. And so this is a cis pent2ene. Right? And here it is CH3CH2 and this alkyl is opposite to this alkyl. So it is trans pent2ene. Clear? So what about the one more, that is hex3ene? This is my structure which I have drawn, linear structure. Putting here it is CH3CH2, CH3CH2. Both are similar on the same side. So C is hex3ene. This is opposite. So trans hex3ene. Now here one thing is to be understood, that there is example but2ene, pent2ene, hex3ene. Each time see what happened. Here on the same side only similar alkyl, methyl. Here what happened? One ethyl, one methyl. So what happened? Functional group increased. Here both ethyl. So here one more functional group increased. Right? So what is the thing? As group increases, the stability decreases. This is little difficult to understand, because as we understand that if something increases in size, then their stability should increase. If more force is there, if more support is there, then the stableness should increase. But here why it decreases, let us see. I just told when I explained with the pen that there is a restriction in the rotation. This restriction is due to some obstacle, right? And that obstacle is responsible for the stability. So the stability of order, if we say, then but2ene with the smallest attachment is higher stable to pent-ene, and pent-ene is still higher stable to hex3ene. The decrease in stability due to increase in group size is due to the steric hindrance. What is steric hindrance? When I saw you in the video that the bonds were not able to move further or were not able to rotate further because of the obstacle of each other, because of the obstacle of the electron clouds of each other, then that obstacle is termed as steric hindrance. So steric hindrance means as group increases, the rotation will experience obstacle. Right? As group increases, so size increase. So double bond will still not get more space to rotate. Whatever the smaller space was there, now that also will be under hinder. And due to that, the stability of the compound decreases. Clear? So I hope up to this you would have understood. Please go through it, read it properly, so you will easily understand. Try to do more and more practice for the compounds, which will help you to understand properly. Thank you.